we use in our chemical reactions are these: hydrochloric acid, sulfuric acid, and nitric acid, right? So if we are using hydrochloric acid, we will get chlorides. And if we're using sulfuric acid, we will get sulfates. If we're using nitric acid, we will get nitrates, so on and so forth. Now, where does the metal come from? Now, the metals can come from a variety of sources. One is from the metal itself. That's easy. For example, copper can react, okay, with, okay, not copper, but okay, sodium can react with hydrochloric acid, right? And then we can give you sodium chloride, right? So one is metal. We will discuss the metal. Wait, we will discuss today metal and carbonate, okay? Because these two we already discussed in the last class. In the last class, we have already discussed the reaction of oxides and alkalis. By the way, the reaction of oxides and alkalis is neutralization. Well, the reaction of carbonate, okay, the reaction of carbonate with acid is also an example of neutralization reaction. What is a neutralization reaction? Yes, hydrochloric acid is highly reactive, but we use dilute. We use dilute version of it. And also we are careful with warming. We only warm a little if we have to, otherwise we don't warm. And we have to follow the safety precautions. But it is a very common acid, okay? So can anybody tell me what a neutralization reaction is? What is a neutralization reaction? When acid and alkali react together? Is that it? Is that it? Acid and alkali reacting together? Acid and alkali reacting together to form salt and water. Mention that as well. To form salt and water, okay? So if what is an acid? Acid is a substance that gives hydrogen ions when dissolved in water. And what is a base or an alkali? Base is an hydrogen ion acceptor or a proton acceptor, something that accepts the proton to give water, right? Yes, this is the ionic equation for neutralization reaction. This ion comes from the acid, this comes from the alkali or the base. Yes, alkali. If it is aqueous, that means it's soluble. That makes this alkali and then give us molecular water. So these are charged particles and this is molecular, right? So you got the main idea, right? So the metal can come from the alkali. Oxides are also bases, okay? They can also form, if they are soluble, then they can dissolve in water to give you hydroxide. So they can also behave as alkalis. And therefore their reaction with acid would be a neutralization reaction. Carbonate, now let's talk about carbonate and metal. Okay. Acid plus carbonate. Now carbonate ions, of course, a reaction with acid and carbonate. Acids will contribute hydrogen ions in the reaction, and carbonate will contribute the carbonate ions. Okay, that's okay. That's fine, Muhammad Wali. Carbonate ions can accept hydrogen ions from acid to form salt. Now, because carbonate ions can accept hydrogen ions, it is behaving as a base, right? So for example, I got this example from your book. Copper carbonate reacting with hydrochloric acid to give, now we know that the insiders react together and then the outsiders react together, right? So H2CO3. Now H2CO3 is an unstable compound. Let me write it down here. H2CO3 is an unstable compound and it readily breaks down into water and carbon dioxide. So the end products that we get are carbon dioxide gas and water and this salt. This salt is metal comes from the carbonate. As I told you, metal comes from the carbonate. Metal comes from the carbonate, right? And the anion is again coming from the acid. So acid gives the anion of the salt, right? Now, most of the carbonates are insoluble except for sodium, potassium, and ammonium carbonates. Now, the solubility of salts, I'm not sure if it is included in your for your exams, but nevertheless, you know, it's helpful to remember. Okay, carbonates, you remember group 1 and 2 metals are highly reactive and therefore their compounds will be highly soluble. Remember this, group 1 and 2 of periodic table. Metals are highly reactive and therefore their compounds or their salts are highly reactive along with this ammonium. Okay, so all other carbonates are insoluble except for sodium and potassium. They are in group 1, and ammonium carbonate. So if you're using any other carbonate other than sodium and potassium and ammonium, then that will be insoluble and we will write solid. In the state symbol, we will use solid because they will not dissolve, and so they will exist as solid within the solution, right? Now then I generalize this equation. Okay, so metal with carbonate reacting with the acid, right? Acid will be donating the anion to the salt, and carbonate will be donating the metal component of the salt, and carbonate ions themselves will react with the, this is the net ionic equation for the whole reaction. So basically, if we remove the metal and the non-metal and the salt, and we just talk about the ionic equation of this reaction, then the carbonate ions react with the hydrogen ions to give us carbon dioxide and water. This is the net ionic equation for carbonates reaction with acid. Carbonates reaction with acid. Okay, what is an ionic equation? I don't think you guys have, I don't think the ionic equation is even included for your exams, maybe not. So I won't confuse you with this. Okay, now tell me something. This is the basics behind this reaction of carbonate and acid. Now, when we will perform this in the lab, when we will perform this actually practically in the lab, tell me something. How will I make sure if in the conical flask, look at this picture, you have done it in the copy. Okay, this is a conical flask and I have a measured amount of, I have measured amount of hydrochloric acid, and they have given us 25 cm cube. So for example, I have 25 cm cube of hydrochloric acid. Sorry, here in this beaker, not the conical flask, here in the beaker, if I have the 25 cm cube of hydrochloric acid and I'm adding copper carbonate, for example, how will I make sure that all the acid has reacted? Because remember, at the end, I only want the salt. I only want the salt. I do not want the other. Remember, we are not only preparing the salt, we are also isolating the pure form, the crystalline pure form of the salt. So our preparation methods should also ensure that at the end, we have pure solid crystals of salt. So tell me, how will I make sure that all my acid reacts with all the copper carbonate and that I do not have any of these left over at the end with the salt? Because remember, carbon dioxide is a gas, it will go out, it will escape, so I don't have to worry about carbon dioxide. And water I can get rid of by evaporation, but if I have any of these left over, that would be a problem. So how will I make sure that all the acid has reacted with all the carbonate? Yes, somebody answered in the chat. And oh, you have done it in the copy, the ionic equation, until it stops fizzing. Right, right. And why was it fizzing at the first place? Why was it fizzing? What was the fizzing about? Yes. Why was it fizzing? Yes, because of carbon dioxide. Yes, Muhammad Wali, good job. Yes, because of the gas. So whenever you have gas as one of the byproducts, of course, as gas is less dense than water, than the solution, therefore it will be in the form of bubbles that will be rising towards the surface, and that's why we will see a lot of bubbling, and that bubbling is called fizzing. Right. So remember I told you that it is easier to separate solid from liquid compared to uh, separating liquid from liquid, especially if they are soluble with each other. So this is solid, right? And this is aqueous solution. So can I use this in excess? Can I use this in excess in order to make sure that all the acid has reacted? So there are two ways in which we can make sure that all the acid has reacted with the carbonate. One is to follow the fizzing. Once the fizzing stops, then I know that the reaction has stopped because no more carbon dioxide is being produced. So I know all the acid has reacted. Is there any other way other than fizzing? Is there any other way I can make sure that all the acid has reacted with the carbonate? Yes, we will add excess of carbonate. And how do we know that I'm adding excess? How will I know that I'm adding excess? No, 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 no. Yes, good job, Wajiha. When it will start settling at the bottom. Why? Because settling at the bottom will tell me that no more carbonate is reacting with the acid, because if it would react, it wouldn't be visible. If it would react, it would give rise to these products. I would not be able to see it settling at the bottom. The fact that I can see it at the bottom is because it is not reacting anymore. And so it's not reacting and it's just simply settling down at the bottom. So as soon as I see this carbonate settling at the bottom, I know all the acid has reacted. Now, no more acid molecules left for this extra copper carbonate to react with. So I will start seeing this excess of copper carbonate. And is that a problem? At the end, how will I get rid of, how can I get rid of this? If there is less acid, so the carbonate will be left, right? Yes. Yes, we can filter it. Exactly. Good job, Wajiha and Riyaz. Good job. Yes. Because this is an insoluble salt, so it won't dissolve. And so I can easily filter it out. And that's exactly what they're doing in this picture. After they have used excess of copper carbonate, and after the reaction has stopped, the fizzing has stopped, now they want to get rid of this excess, and so they are filtering. Now, in the filtrate, what do we have? Right. Now, in the filtrate, what do we have in the filtrate right now? So we have removed copper carbonate. We have removed copper carbonate by filtration, the excess of it. All the acid has reacted, so we don't expect any of the acid left behind. So basically, we have gotten rid of both of these reactants. Now, I expect only copper chloride with water, because remember, even the fizzing is stopped. So all the carbon dioxide gas must have escaped through the bubbles coming on the surface. So I expect only copper chloride and water in the filtrate. And luckily we did not use any indicator. Why didn't we use an indicator here? Why didn't we use an indicator here? Why didn't they use an indicator? Any ideas? Anybody knows why didn't we use an indicator? What? Because it will stop reacting. What will stop reacting, beta? What will stop reacting? The color will not change. No, the color should change because it is a neutralization reaction. You had acid and now you have neutralized. So there would be color change if you add an indicator. It would be, if you're using universal indicator, the color would change from red to green because this is neutral. So the color in neutral is green, but we are not using any universal indicator. No, no, Muhammad Wali, no, it won't stop the reaction. It won't. The reaction would go on. See, what is the purpose of an indicator? Why do we add an indicator at the first place? Why do we add it? Think about it. Did we need it here? The question is, did we need an indicator here? And what is the purpose? Why do we add an indicator? Yeah, okay, but tell me, why do we add an indicator? To see if it's alkali or acid, to see all the acid and alkali are used up. Exactly, yes, Hassan. Yes, we add indicator to make sure that all the acid has reacted. That's why we add indicator, because we don't want excess of any of the reactants left over unreacted at the end along with the products. Yeah, so the purpose of adding indicator, remember, the purpose of adding indicator is to know when exactly all the acid has reacted with all the other reactants, so that we do not have any leftover unreacted acid or alkali at the end. So when the indicator gives us the neutral color, we know that none of the acid or the alkali is left over. So we have only the neutral products. That's why we add universal indicator. But in this particular reaction, we can easily find that out without using an indicator. That is by following fizzing. When the fizzing stops, we know the reaction has completed. And also we can easily add excess of it. When it will start settling at the bottom, we would know that the reaction is complete and we can filter it out. So we don't need to use a universal or any sort of indicator, okay? If we did use an indicator, here, despite all these signs of the completion of reaction, then we would have to get rid of that indicator as well, because we want pure salt. We don't want any drops of indicator either in it. And how can we get rid of an indicator? If we have added indicator, but we don't want at the end, because at the end we only want pure, yes, Wajiha, good job. Then we would have to use charcoal powder to get rid of the indicator. And then how can we get rid of the charcoal? And then how can we get rid of the charcoal powder? So, okay, you added charcoal. Charcoal absorbed all the indicator, yes, by filtration. Good job, Wajiha, good job. Yes, Wajiha, you're answering very good. I'm happy. Yes, yes, yes. So, yes, so we would have to then get rid of charcoal. So that's, these are extra steps. Why to take extra steps when you can do without it? You don't need a universal, you don't need any sort of indicator, right? So that is why we did not use any indicator in this particular reaction. If anything is left, we can use that leftover again. Well, then you should know exactly how much is left over so that you can add exactly that much acid. And that is difficult. How will you know how much is left over? Right? That's the problem. So if, for example, you have 2 cm cube of acid unreacted left, but how would you know that it's 2 cm cube? Because you need half the amount. Can you see? 2:1. Only one molecule is reacting with 2. So you will have to halfen it up. So if 2 cm cube is left, you want 1 cm cube of this. So that is difficult. Yeah, it is difficult. You will have to repeat the experiment. Okay, because you'll keep adding and you'll keep subtracting, and then you won't get the pure thing, right? So you will have to repeat the experiment, right? But that's a good question. Okay, so you understood, right? Okay, so that was that. Okay, okay. Now, should we heat this? Should we use heating in this experiment? Yes or no, and why? Should we heat this reaction? Do you think we should have used a heater or some heating source? Not a heater, but a heating source. Yes. Yes, it is reactive, first of all, yes. And secondly, yes, can you also see that one of the products is a gas? One of the products is a gas. So if you heat it, the rate of reaction will increase and it might go out of control, and you might have an accelerated rate of gas production that might be explosive, might lead to splashing of the whole solution, and you're dealing with a very strong acid here, and it might be dangerous in a lab. So you don't need heating. The reaction is so spontaneous. I mean, this reaction is so easy to take place that even absorption of heat from the surroundings will be enough for this reaction to go forward, right? Okay. So it's heating would be explosive. Heating would be dangerous. Okay. Okay. Another question. Could we have used excess of carbonate if the carbonate was soluble? Now remember I told you sodium and potassium carbonates, because they are group 1 and 2, sodium and potassium carbonates are soluble. So if, for example, I had used sodium carbonate instead, now sodium carbonate is soluble, it would be aqueous. So then could I have used excess? Could then I have used excess, Wajiha? You were saying yes. Why? Then if I would add excess, would you see it settling at the bottom? Because it's soluble, it will dissolve. Would you see it settling at the bottom? It's soluble, right? It will dissolve. Yeah, no, you won't be able to see it. And then how would you know that the reaction is all the acid has reacted? Even if there's no reaction going on, it won't settle at the bottom because it is soluble. And that would be a problem. So what should you do instead? So that you cannot add excess, because then leftover or the unreacted would stay in the solution form and you wouldn't know, and it would contaminate your salt. So you would have some unreacted leftover sodium carbonate along with sodium chloride. I mean, if you're using sodium carbonate, the salt you'll get would be sodium chloride instead of copper chloride. So then what would you do instead? What would you do instead? Let me write that equation down. If, for example, I'm using sodium carbonate with hydrochloric acid, I should get sodium chloride plus carbon dioxide plus water. And is this, yeah, now it's balanced. Okay. Then this would be aqueous and this would also be aqueous. No, then we cannot use excess. Okay. Then we will use titration method. Titration method that I discussed in the last class, in which you take a measured volume of the acid, okay, in a conical flask, and then you use a burette. You use a burette, okay, you use a burette, and in the burette you can use sodium carbonate, and then you will add measured amounts of sodium carbonate, and then yes, you will use an indicator. Then you will use an indicator, or you can even follow the physics. Yeah, you can even follow the fizzing. As soon as the fizzing stops, you stop adding sodium carbonate. But you will use a burette so that you know exactly when to stop. And you will add very gradually, drop by drop. So that's the difference in methods depending upon what sort of reactants you're using. So if you're using a soluble carbonate, your method would change, okay? And this is called titration. Titration is when you are adding measured amounts, when you are adding gradually and you are following the reaction. That's called titration, okay? This would be titration. And titration is a method of reaction when the reactants both are soluble, when both the reactants are soluble, okay? This is, okay. Okay, then. How do copper 2 chloride crystals look like? What do copper 2 chloride crystals look like? They are rectangular. Okay. What about the color? I'm sharing my screen. I'll show you. I got picture. Let me see. Okay. This is copper chloride right before, I mean, soon after its preparation with no water in it, no water molecules dissolved in it or added to it. Now, when the water molecules are absorbed by the crystals, they become blue-green like this. Or if they have bonded with more water molecules, the green color gets darker and you see this grass green. And yes, Vajiha, you are right. The shape looks rectangular to me. Right. Okay. Now, let's move on to the reaction between metals and acids. Now, you must have done metals in periodic table, right? You must have done metals in the periodic table. And have you done the reaction of metals with acids? Well, metals reaction with acids was similar, because in reaction with metals, oh, you guys haven't done periodic table, metals. Okay, I remember my daughter did when she was in grade 6, and I remember she did it in first term. Okay, so metals, if you haven't done, then maybe I shouldn't take example of, you did? Okay, so okay, metals react with water in similar way, in the same way as they react with acids, right? Now what happens? Metals react with water to form metal hydroxide, alkali, and hydrogen gas. Do you remember? Metals react with water to give alkali, which is metal hydroxide, like sodium hydroxide or potassium hydroxide, and also release hydrogen gas. So similar reaction takes place here when metals react with acids. Again, if the metal is more reactive than hydrogen. So you will need a reactivity series here. You will need reactivity series here if the metal, remember this is a big if the metal is more reactive than hydrogen. And how would you know if a metal is more reactive than hydrogen or not? You will have to refer to the reactivity series. Now, reactivity series might be given in your book, and it is also available on Google, and I will also share with you. The metal, if it is above hydrogen in the reactivity series, meaning it is more reactive than hydrogen, or you can look at it as being stronger than hydrogen, it will kick the hydrogen out and will make a compound with the anion itself. And so it will make a salt with the anion. So now this is a salt, and hydrogen atoms or hydrogen ions have been kicked out, and the hydrogen has formed a diatomic molecule, okay, to be stable, right? Now, my question is this a neutralization reaction? Why or why not? Is this a neutralization reaction? Do you think it's a neutralization reaction? Neutralization reaction is this: hydrogen ions being accepted to form water. So are you having that here? We have hydrogen ions here, okay, but is anybody accepting these hydrogen ions to form water? No. Yes, no. We do not have any hydrogen ion acceptor to form the water molecules. So this is not a neutralization reaction. Okay, what sort of a, okay, you have not done that. So, okay. Should we be heating this reaction? Should we be heating this reaction? Why or why not? Okay, good. Why, Muhammad Wali? Why? Muhammad Wali said that no, we should not be heating this reaction. And so why not? Because yes, this also is a very powerful reaction. Yes, this is a strong reaction. Yes, another thing, there's gas coming out. So if we heat it, we are increasing the rate of reaction, and therefore we are increasing the rate of this gas, increasing the rate of production of this gas. And so there can be splashing, splurting. like a little, you know, sort of explosion. If you go too overboard, there can be even some explosion, and you don't want this strong acid splashing onto your face or eyes, right? Because, and then you know, this would be dangerous. This is not safe. So that is why no need of heating. Again, this will also absorb energy from its surroundings, and yes, it will absorb energy from its surroundings, and that would be enough to make this reaction go, right? Okay. Now, my next question is, which acid or metal would you use to make iron sulfate? Which metal and which acid will you use to make iron sulfate? Which metal and acid would you use to make iron sulfate? Any answers? Am I getting any answers? Let me see. Acid is sulfuric and metal is iron. Good job, Wajiha. Good job. Yes. So we can have iron plus sulfuric acid to give us iron. So iron will, can iron kick the hydrogen out? Can iron kick the hydrogen out? How do we know? Let's look at the reactivity series. I'm sharing my screen. Let's look at the reactivity series. Look at this. I made this reactivity series. You can even find it on Google. Okay, maybe also available in your book. I don't know the page number though. So I have separated hydrogen and carbon with the help of two lines. Why? Because this reactivity series is of metals only. This reactivity series is of metals only, and carbon and hydrogen are not metals. But we usually compare their reactivity with carbon and hydrogen due to the reactions that we study, right? That is why I wrote down carbon and hydrogen, but I separated them because I want to compare the reactivities of the rest of the metals, especially with carbon and hydrogen. So if I see a metal above hydrogen, I know that that metal is more reactive than hydrogen, and so it would be able to kick hydrogen out of compounds in reactions. Okay, same is the case with carbon as well, but we will stick to hydrogen, okay? And you can see that the reactivity is decreasing down this series. The reactivity is decreasing down the series. So the metal at the top is most reactive, which is potassium, we can see. And the metal at the bottom is the most unreactive, almost inert, which is platinum. You can see gold, silver, platinum are at the bottom, right? So now we are dealing with iron with sulfuric acid, right? So is iron above hydrogen? Yes, it is. So that means iron is more reactive than hydrogen, and so it can kick hydrogen out and make iron sulfate, right? Iron to sulfate, and hydrogen gas will be the byproduct. And is this balanced? H2SO4, but I need 2 of iron here. Yes. Yes, okay, Jazakallah khairan Fawad. Yes, the diagram is present on page, according to Fawad, it is page 138, chapter 10, reactions of metals in the new book. Okay, Jazakallah khairan. Okay, what about what metals and acids would be used if I want to prepare zinc chloride? If I want to prepare zinc chloride, what is the highest reactive gas? I think fluorine. I think fluorine. Fluorine because it is highly electronegative. Fluorine, FluO. Fluorine is even more reactive than chlorine. Because remember, in halogens, in nonmetals, the reactivity decreases down the group. So so fluorine is above chlorine, so it's more reactive than chlorine. Okay, now tell me, what acid or metal would I need to make zinc chloride. Good job, Wajiha. Good job. Wajiha, you're really good in chemistry, mashallah, mashallah. So zinc reacts with hydrochloric acid. So can zinc kick hydrogen out? Is zinc more powerful than hydrogen? Are you sure? Okay. Then yes. Okay, good job. And then we have hydrogen gas being produced, and to balance it, 2H2Cl, so 2HCl. Okay, can I use acid and metal to have copper sulfate? What acid and metal should I use to make copper sulfate? Can anybody tell me? Metal, which metal or acid can I use to prepare copper sulfate? Ah, Wajiha, I got you. Hassan, I got you. I tricked you. I tricked you. I tricked all of you. Beta, can copper kick hydrogen out from sulfuric acid? Look at the reactivity series. Let me share. You can also look at your book, but I can also share. Yeah, I am sharing my screen. Am I not sharing my screen? Okay, sorry. Okay. Here, where is copper? Is it above hydrogen? No, it's below hydrogen. So do you still think copper will be able to kick hydrogen out of sulfuric acid to form copper sulfate? No. And when they give you multiple choice questions like that, then you get tricked. So remember, just because you can write an equation does not mean that that reaction can take place. Before you write a reaction, before you decide on your final answer, ask yourself, does this reaction actually take place or not? Compare the reactivities, okay? Think if that molecule exists, that product exists or not, and all of these factors, and then decide on your final answer. Okay, so no, this reaction cannot take place. We cannot use a metal and an acid alone to prepare copper sulfate. Okay, so no, this reaction cannot take place. Okay. Okay, so what is, yes, copper is less reactive. Yes, good job, Fawad. Okay, so if we cannot use a metal and an acid to make copper sulfate, how can we prepare copper sulfate? Do you remember? How else can we prepare copper sulfate? Do you remember from your last class we discussed? What can be the other methods of preparing copper sulfate? Who remembers? Direct combination? No. Direct combination, how will you have sulfate alone? Sulfate is an anion. It's a polyatomic anion. You cannot have just sulfate lying there. Direct combination can be used in case of, salts like iron sulfide. So iron and sulfur, you can add them and heat them together and you can get iron sulfide, but not in this case because this is a polyatomic anion. Titration of which two? Okay, titration of which two? No, not titration. You guys don't remember? Okay, flip your books. You prepared for the test. Remember last week, same day you had a test. Yes, copper oxide and sulfuric acid. Good job. Yes, and this is not titration. Is this titration? No. Why isn't it titration? Why isn't the reaction of copper oxide and sulfuric acid not a titration? Are we measuring the reactants and then adding with the help of burette? Are we doing that? No, and why not? Because who's gonna answer? Why is this not titration? Why is the reaction between copper oxide and sulfuric acid, not titration. Titration meaning we are not using burette, we are not adding measured amounts of any of the reactants drop wise. We are not doing all of that. Why? Because, come on. Yeah, why are they not measured? That's my question, Wajiha. Think harder, come on. See, copper oxide is what? It is an insoluble solid. Where did the picture go? Yeah, here. Yeah, no, because copper oxide is insoluble. So it is in the solid form. If it is in the solid form, we can just remove the excess. We don't need to titrate. Because copper oxide is insoluble, it is in the powder form, we can easily remove by filtration. We will just see when it will start settling at the bottom, we know the reaction is complete, we can filter it out. Simple. That's why we don't use titration. This is not titration. We don't need to use burette. Remember, titration is only used when both the reactants are soluble. When both the reactants are soluble, because when both the reactants are soluble, you cannot add excess, because then how will you remove them? You cannot remove the soluble reactant by filtration. So it will be hard and you will have the leftover unreacted in the final product, and that will contaminate your salt. So that is why we use titration, right? Okay. So you have to know that copper oxide is insoluble. Now, it helps a lot if you know which salts are soluble and which are not. It helps tremendously in choosing the methods. Okay, the solubility, you will on YouTube, you will find a lot of helpful videos on how to learn the solubility of salts. Okay, and it is given on page, this is the page in my book, 133, Solubility of Salts. Okay, there are many videos on YouTube which will help you remember which salts are soluble and which are not. Keep asking yourself this list every day, and after a week or so, you will remember it. Okay, it's not that hard. Yes, in the beginning it is hard, but once you keep doing it every day, you will remember it, and it will help you a lot. Okay, now this answer that this question that I just asked you, it depended on the fact whether you know that copper oxide is soluble or insoluble, whether it exists in the powder solid form, whether it will dissolve or not. If it is soluble, you will use titration. If it is insoluble, you will just use excess of it and filter out. Okay? Okay. Now this last page, acids need water. Now, I have talked about this in great detail in the beginning of this chapter. Why is it that acids need water? Because acids are substances that give hydrogen ions when dissolved in water. If you do not dissolve acid in water, it won't give hydrogen ions. And if it doesn't give hydrogen ions, then it is not an acid, because it is the hydrogen ions which are actually carrying out the neutralization reaction, right? The ionic equation, it was the hydrogen ion that is carrying out the reaction, and in the aqueous form. So it has to dissolve in water. So if you do not provide the acid with water, there will be no hydrogen ions and there will be no neutralization reaction, right? So they carried out this experiment and they are comparing pure solid citric acid, okay? Compare solid citric acid, which has no water added to it, pure citric acid with no water, and results for citric acid solution. So they're comparing pure citric acid solid with the citric acid solution. And what are the tests they are using? They are using the indicator test, and they are also using their reactions, the acids reaction that we just studied, acids reaction with metals, magnesium ribbon, acids reaction with carbonate, okay, and they're using sodium carbonate. Now, sodium carbonate is soluble, as I just discussed with you, but we are not preparing salt here. We are just comparing the results, so we don't need to worry about titration and all of that. Then they are not using any neutralization reaction here. Can we use neutralization reaction to test if the citric acid, solid citric acid, and citric acid solution are acidic or not? Well, yes, we might. We can use neutralization reaction as well, but again, we will use indicator. Okay, indicator to indicate to us when the reaction is complete and when do you have neutral salt. Okay, conduct electricity. Why are they using the conduction of electricity to compare the two? Okay, first, before I talk about the conduction of electricity, first let's do this table together. Okay, let's do what we already know. Test for acid, result for pure solid citric acid, blue litmus paper. What will I see? What will be my observation? Let's do this table together. Red color with pure solid citric acid. Wajiha, with pure solid citric acid, you will see the color change to red. Pure solid citric acid and with citric acid solution. Red with what? Pure or citric acid solution? See, we are comparing. We are comparing the solid pure citric acid with the citric acid solution. With pure, it would turn red. Yes, Wajiha. With solution, it would. But what about red with pure? No, Muhammad. Hassan Wali, no. Not with pure. Why? Why not? Because this does not have any water. If there is no water, no hydrogen ions released. So blue litmus paper will remain blue, nothing. Okay. With the solution, we will see the blue litmus paper turning red. Only with the solution, because solution means there is water. And so in the water, the citric acid would dissolve as this acid and will give away hydrogen ions. Remember I talked about this hydrogen chloride breaking into its ions when dissolving in water? The reason I'm not explaining this to you in detail is because I've already explained it. So if anybody is interested, you can listen to my recording, the first recording on this chapter. The first class, I talked about why acids give hydrogen ions in water. Right? So only in solution, the acid will give hydrogen ions, and those hydrogen ions are responsible for changing the color of blue litmus to red. Okay. What about sodium carbonate? What will you see with pure solid citric acid? Pure solid citric acid. There are no hydrogen ions here. Yes. Come on. Nothing. No reaction because no hydrogen ions. No reaction because no hydrogen ions. No reaction, no conduction either because no ions, no mobile ions. For conduction of electricity, you need, I will talk about this in detail afterwards. And what will you see with this solution? With the solution of water, you will see all the acidic properties because the hydrogen ion is released. Right, yes, Hassan Wali, yes. There won't be a reaction because there, even if there are a few ions, but they are in solid form. They are not available for reaction. For a reaction to take place, you need the ions to be mobile, to be free. And that is possible only when they dissolve in water. That's why we are comparing. What is the purpose of this experiment? What is the purpose? We are trying to prove, can acid behave as an acid without water? That's the purpose. We are trying to see if an acid behaves as an acid without water. So no, the pure solid citric acid, because there is no water, it is not giving any of the reactions of acids. But yes, the solution, of citric acid with sodium carbonate will release carbon dioxide. Okay, so fizzing due to carbon dioxide. Yes, fizzing due to carbon dioxide. Magnesium ribbon, again, fizzing due to hydrogen gas. Fizzing due to hydrogen gas. Okay, do you know the identification tests for these two gases? Do you guys know the identification tests for carbon dioxide and hydrogen? Who will tell me the identification test for carbon dioxide and hydrogen? Matchstick? No. Have you done the identification tests? For hydrogen, it gives a pop sound with a lighted splinter, and carbon dioxide turns lime water milky. Have you done that? No? Oh, okay. Okay. Now your book is asking, can you think of another test for acidic properties other than these? Can you think of any other? Can you think of any other? Litmus paper is already mentioned. Litmus paper is already mentioned. We can use an insoluble base and then see if the neutralization reaction takes place, and does the indicator turn color? We can do that. Or we can use a pH meter. pH meter is an electrical instrument device which gives us the pH of the solution in the form of a digital digital instrument. Okay, now let's talk about conduction of electricity. Now, conduction of electricity. See, when you have hydrogen ions or hydroxide ion or any ion for that matter, which is dissolved in water and therefore it is mobile. Mobile meaning it is, for example, hydrogen ions are available and they are mobile. They are free to move. They're in the liquid form. That means they can conduct electricity. Electricity can only be conducted if the charged particles are free to move. Now, when the neutralization reaction is completed, we don't have any hydrogen ions or hydroxide ions left over because they have canceled each other out to form the water molecule, the neutral water molecule. Now, water molecule is not charged. It is a molecule. Water cannot conduct electricity. Pure water cannot conduct electricity. So therefore, when we see that a solution is conducting electricity, so we know that the neutralization reaction has not completed. Once the neutralization reaction has completed and we have neutral water molecules, then that is an evidence that neutralization reaction has completed, and now we have only water molecules. So that is why conduction of electricity is also used as one of the methods of finding out if the neutralization reaction is taking place or not. So here, the citric acid will dissolve in water and will release hydrogen ions, and so there will be conduction of electricity because hydrogen ions are available in the dissolved form to conduct electricity because they are mobile and there are hydrogen ions released here. Now, because there is no water here, this is in the solid pure form, there are no mobile hydrogen ions, and therefore pure solid citric acid cannot conduct electricity. Okay, I hope I cleared this point. Okay, another last thing, I have discussed this whole portion of this page except for the fact, now again they are comparing hydrogen chloride gas with the dissolved form of hydrochloric acid in which the hydrochloride gas has dissolved in water. So first it was simple molecule, simple covalent molecule. This was not charged. There are no ions here. It's a simple molecule. Therefore, it cannot behave as acidic. It will not turn blue litmus paper red, and it will not show you any of the acidic properties. But when we dissolve it in water, it dissociates, meaning it breaks. Dissociates meaning breaks. It splits up, dissociates into its ions, and therefore releasing hydrogen ions and chloride ions. Now hydrogen ion is available to turn the blue litmus red, right? This is what they're trying to show, that that same gas which was not giving you acidic properties, after dissolving in the water is giving you acidic properties. So that shows how important water is for acids to be acids, right? Now there's a question here. Why is a funnel used when dissolving the gas? So I wanted to discuss this question with you. Why is a funnel used when dissolving the gas? Any ideas? Any guesses? It's okay if you're wrong, but any ideas? So it doesn't, the gas doesn't go away into the air? Okay, couldn't we use a simple, so it can go direct way. Okay, couldn't we use something like this, like a simple tube, and then introduce hydrogen chloride gas directly? Why did we use a funnel? Why did we have to use a funnel? What is this importance of using the funnel? Could we use a simple tube like this? Okay, it has more space for what? Why does it need space? Yes. Okay. For turning into water. See, as the gas is introduced, if for example, I use this tube, to react more, it needs more space. Okay, it's not reacting, it's dissolving. Okay, it's dissolving in the water. See, it's dissolving in the water. It's dissociating into ions. Okay. Well, you can call that a type of reaction, but okay, so as the gas, okay, as the gas is being introduced, if for example, I use this tube, and as the gas is being introduced, and as it will dissolve in water, so the volume of gas will decrease, right? Because the volume is getting dissolved in the water, leaving behind some space or vacuum. And so because of that vacuum, there will be a little suction of the water up. Okay, we don't want that happening. We don't want that. In order to avoid this suction of water up, we use a funnel. In the funnel, the water will not be sucked up because the funnel's mouth is wide. Another advantage of using a funnel is that it is providing greater surface area. So more molecules of water are in contact with the gas, and so easy dissolving, right? And faster dissolving. So these are the two advantages. One is that it prevents the sucking up of the liquid, of the water. Second is that greater surface area is available for the gas molecules to dissolve with the water molecules, right? Okay, now the time is up. I wanted to do the end of chapter questions. I will go through your scheme of studies. Okay, I have free time this Thursday from 4 to 5 again, same time. So I was thinking that we start with the past paper questions and also the further questions within this book and the end of chapter questions. And basically we will do questions together. So if you are interested, I can arrange for a class in which we will purely solve questions. Okay, so okay, then inshallah this Thursday from 4 to 5 we will do end of chapter questions of this acids and alkalis, and I will also see if you have preparation of insoluble salts included or not. I will check in your scheme of studies. If it is included, then we will complete this and then move on to the end of chapter questions. We have done a few of them, but I think a few are left as well. And then we will also solve the further questions. Okay, you guys have a test on Thursday? Yes, questions on Thursday, right, 4 to 5. If you guys have a test, please let me know. Then I can reschedule it for next week. Then next week it would be the same day. Okay, solubility of salts is also coming in the revised SOS. Oh, okay. Okay then. Okay, then we will finish that part. Okay, we will finish the solubility. Then, okay, next week, do you guys have a test on Thursday? You want the next class on Thursday or next week? Please let me know. Maybe a few sections have a test, so don't get confused. Maybe a few of you have test Thursday. Okay, Hassan Wali is saying that he wants the next class to be on Thursday. Okay, Thursday. Okay, so Thursday it is. We will complete the chapter. We will do the end of chapter questions and the further questions. Okay, inshallah, same time, 4 to 5 p.m. Okay, is there any question you guys want to ask regarding the lesson? If there is question, then let me know or raise your hand. Okay, let me. Is there any question?
Yes, actually, like, what are cations? I still don't understand.
Yes. Okay. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.